We now want to give a more in-depth discussion on the topics of center of mass and moment of inertia and how to calculate these and what they are. But first, before we dive into all of the particulars, let's talk about this word moment for a moment. Okay? So, in physics, a moment is the product of some variable, and this variable will be some physical variable about your given object or system of objects, system of particles, if you will. Um, Multiply, or it's the product of that variable and um, a distance from an axis of rotation. So you have to specify the axis about which you're going to be rotating for a moment to have some sort of meaning. But with that in mind, torque is a moment because it is defined as R cross F, which is some distance about an axis of rotation multiplied by some variable relevant to your system. In this case, the force that's applied to it. Okay. But then you have moments that are of this form. Okay. And I'm going to label these m sub n. So this is the nth moment of quantity m, or the nth moment, is equal to the integral of r to the n, where r is again your lever arm, times dm. Okay? And dm is a infinitesimally small mass piece of your system. Okay? So the zeroth moment, if we let n equals 0, then your moment, your zeroth moment, equals the integral of r to the 0 dm, which is just the integral of dm, which is just your total mass. Okay? So the zeroth moment, when your variable is mass, okay, then your moment is your total mass. If n equals 1, then your first moment of mass is equal to r to the 1 dm. And this is a 1, not a prime. Okay. And I guess I really should specify a capital M down here, indicating that this is over the entire mass. You have to integrate over the entire mass. Now, this quantity by itself isn't a terribly useful quantity in and of itself, but it does appear in the calculation of the center of mass. Okay. So this is the numerator in the center of mass calculation. And finally, if n equals 2, now these are the three that are going to be the most important for us. Now, of course, you can take higher moments, but for our purposes, n equals 0, 1, and 2 are the ones that we care about. So your second moment is if I have r squared dm, and this is your moment of inertia. Okay. We're also going to give this the letter I. Okay, that's the symbol that we're going to use in our equations. But this is how you calculate moments. Now, of course, you could extend this out to r cubed dm, r to the fourth dm, and so on and so forth. But these are the ones that we are going to be using in our cases. Okay. Now, we're going to start with the center of mass. And to start with this center of mass, you'll notice that the first moment is the numerator in the center of mass calculation. So this means this is a fraction. And as a matter of fact, it turns out to be a weighted average calculation. So before we get into how to calculate this, we need to do a weighted average example to understand exactly what a weighted average is. Now, we start with the normal average, and let's suppose these are the results of rolling a six-sided die. Okay. And so I've rolled my die 6 times, trials 1, 2, 3, 4, 5, and 6. And my results are 1, 3, 4, 2, 3, 6. And I want to know what the average of these rolls is. Now, I think that everybody here knows how to do this, right? So what we would do is we would just add up all of the results and then divide by the number of trials, in this case 6. So this is going to be 1 plus 3 is 4, plus 4 is 8, 10, 13, 19. So this is 19 divided by 6, which is 3 1/6. And if we put that in decimal form, that will be 3.16 repeating. Okay, so it's the 6 that's repeating, not the 1/6. So even though our number didn't turn out to be an integer, this should actually make some sense, because if I have a six-sided fair die, then what that means is that I should roll every single number equal probability. Now, with say 10 rolls, I'm not necessarily going to get an equal distribution, not just because 10 is not evenly divisible by 6, but with a minimum of 10 rolls, or even a maximum of 10 rolls, that's just not enough rolls to actually see the statistical nature of a six-sided fair die. It's true that any of the 6 numbers are equally probable, but no one would be terribly shocked if you rolled 3 4s in 10 rolls. It might be a little unique, but if you've ever played Yahtzee, then you know that you can roll 3 4s out of several rolls, and it's not that big a deal. But if I rolled my dice 10,000 times, and out of those 10,000 times, I had 5,000 4s, now that would be extremely interesting, right? But let's suppose I did roll it 10,000 times, and more or less I got what I expected. Each of the numbers was represented roughly 1/6 probability. Then in that case, the average is going to be 3.5, because I have 6 possibilities, 1 through 6, it's an even number, so my average is going to, if it's all fair, then it's going to have to lie right in between my middle two numbers, which are 3 and 4. And so my average over many rolls of a fair dice should be 3.5. So this result of 3.16 for just 6 rolls is very reasonable, right? And so in mathematical notation, what we would say is the average is equal to the sum. So I'm going to say, let's let these results be my variable x. So I'm going to add up all of my x's. And I'm going to let my trials be denoted by an index I. Okay. So each trial is a new index of I. And so what I'm going to do, this would be x sub 1. This is x sub 2. This is x sub 3, and so on. So because each of these subscripts corresponds to an index, I can say I need to sum up all of my x sub i's, where I'm going to start with my index of 1. So I start with this trial right here. And I'm going to add everything up to my maximum number of trials, n. So whatever your last number of trials is, that is your n. This is your maximum number of trials. So I start with x1, and then I go to x2, add x3, add x4, add x5, and then all the way up to x equals 6, or x sub 6. That is my maximum number. And then I divide this by n. Okay, so this is the definition of the simple average. Okay, and this is how you would write it mathematically. So let me actually, as a matter of fact, erase that a little bit. Maybe redraw that box so it's not overlapping with the math notation. So this is your simple average, okay? Written in slightly more statistical formality than, just this, right? But your center of mass is what we call a weighted average. Okay, well, actually, it's not. Well, it is. It is a weighted average. I was about to say it contains a weighted average, but no, it is the weighted average. The numerator is just the first moment, as discussed in the previous slide. But, so how do we calculate a weighted average? Okay, so a common example of a weighted average is your GPA. If you've ever been curious what your GPA is, here's how you calculate it. Okay, so your GPA is going to be calculated from a combination of your credit hours and your grade points. Now, so let's look at this second column first. So if we have a typical 4.0 system, then the highest grade point you can get is 4. And in this system, I'm assuming that our school just grades on A, B, C, D, and F. Okay, grades. Now, many schools, many institutions have the plus minus system, which will give you like 3.666 and 3.333 for pluses and minuses. B plus or 3.666 would be an A minus, 3.333 would be a B plus, 3 is a B, 2.666 is a C plus, and so on. But for simplicity, we'll just assume that our school is very simple and just uses pure letter grades. Now here I have my credit hours that correspond to the number of hours that I have earned at that particular grade. So what this means is that if I look at this first row here, or really this is the second row, and as a matter of fact, let's go ahead and index these. Okay. So if I look at the I equals 1 row, let's actually do look here first. What this is claiming is that I haven't earned any grade points at a 0 credit hour level. And so what that means is I haven't earned any Fs. Okay, I have 0 Fs. I have 0 credit hours with a grade point of 0. So I haven't earned any Fs. But I have 9 credit hours at a D. So this might be, if those were each 3-hour classes, typical classes, then I would have earned 3 Ds on my transcript. Okay. I've earned 27 hours at the C level. So this would be like earning 9 classes with a C. Okay. But I have 45 hours at the B level. So this would be like, 15 Bs, right? So I've 0 Fs, 3 Ds, 9 Cs, 15 Bs, and I also have 18 hours at earning an A. So again, if this is 3 credit hour classes, then this would be like 6 classes with an A. So I've got 6 classes with an A, 15 with a B, 9 with a C, 3 with a D, and no with an F, right? And so to calculate your GPA, what you do is you take each individual index of your credit hours and multiply that by the corresponding grade points. So 0 times 0 equals 0. 9 times 1 equals 9. 2 times 27 equals 54. 3 times 45 equals 135. And 4 times 18 equals 72. So the way you take your weighted average, okay, to calculate your GPA is you take this product of your grade points and your credit hours, and then you multiply each of those by the index, just as we've done. 0 times 0 is 0, so that's your index of 1. 9 times 1 is 9, that's your index 2. So we take each of those products and then we sum them up. Okay, so that's what this number down here is. This 270 represents the entire sum of each product of my credit hours and my GPA, or my grade points per index. And then I divide that by the total number of credit hours. And that tells me what my grade point average is. And in this case, our sigmas, I didn't write it explicitly in our formulas to save space, but our sigmas go from I equals 1, which is my first index, to n equals 5, which is my maximum index. Okay, and so in this case, my GPA, and by the way, I've also summed up my credit hours, so this would be the denominator. So my GPA is going to be equal to 270 divided by 99, which gives me 2.73 to 3 significant figures. So this is a high C average. Okay. Now, in statistical jargon, what you have here, the reason we call this a weighted average is because you're finding the average of a quantity times that quantity's weight. So the credit hours here are your weights. My grade points at each index, 0, 1, 2, 3, and 4, are weighted by how many credit hours I have at each of those levels. Okay, so your weighted average is equal to the product of your weights times your measurements, whatever measurement you're making. In our case, it's grade points, divided by the sum of your weights. Okay? So this is the whole idea behind a weighted average. And, by the way, you'll notice this definition. So I'm going to call X bar my weighted average for whatever quantity X I want to measure. Okay. And in this case, our weighted average was discrete. Okay. So 0, 1, 2, 3, 4, etc., etc. These are integers. But if my variable that I'm interested in starts to become continuous, okay, then that is going to become an integral, okay? So this is for discrete functions or discrete data sets, okay? Whereas my average is going to become an integral if X is a function, okay? And so then my weights are going to be well, they're going to have to be adjusted to fit the functionality of X. But in our case, okay, what is going to happen is that X is going to become a function of usually, well, for our purposes, for mass, center of mass, and moment of inertia, it's going to become a function of position. And your weights are the infinitesimal mass at that position. Okay. And then for the weighted average, to complete the calculation, if your dm is your the weight of each distance x, then I'm going to divide by the total mass. Okay, so we typically don't write this as x of r. We typically write this as RCM. And this stands for the position of my center of mass is equal to my function r. So r is my function. And this is just the distance from the axis of rotation to each little piece dm divided by the integral dm. Okay. And we will work through both the discrete and the continuous data. Okay, so in other words, if this is a function. Um, so to start out, let's actually also rewrite the center of mass for the discrete equation. Okay, so this is the specific form of the center of mass equation for discrete data translated from this general form of a function times its weight. Okay, so this equation transforms into this equation. And notice this is a vector equation in physics. Okay, your weighted average does not necessarily have to be a vector, but in physics, your center of mass is a vector because you always are going to be measuring with respect to some coordinate system, origin, and axis of rotation. Okay, so let's do two examples. Let's think about a dumbbell where I have mass 1, mass 2, and they're connected by a bar of length L. And let's consider the bar to be massless. So this is a really, really light bar compared to the weight of the dumbbells, or compared to the mass of the dumbbells. And further, let's assume that these masses are equal. So this is a true dumbbell. So this is very similar to what you would use if you were going to the gym, with the exception that usually those bars are not massless. But you can put enough weight on them that effectively the mass of the bar stops mattering as far as your weightlifting regime or exercise goes. And it's really just the weights on the end that are doing the resistance for you. Okay, so you can approximate this as just a regular dumbbell in the gym. Okay, so I want to know what the center of mass is. Now, if these spheres are identical, then we would predict that the center of mass ought to be right in the middle. It's the balancing point. That's not necessarily true, but for symmetric situations it is. So our center of mass prediction is that it's right in the middle. So is this true? Oop. Okay, so if we want to figure out where the center of mass is, we first have to identify a coordinate system. So we might as well work right along the x-axis. And here's the crucial part. We have to specify the origin. Okay? So I'm going to put the origin right in the middle. Okay? I'm going to put the origin right in the middle. So x equals 0 right in the middle of my coordinate system. So now I can compute the center of mass. So, actually, you know what? Let's do this on the next slide. It'll be a lot easier. We'll have more room. So, let's redraw this right here, because I'll want to draw my vectors on here. So we'll put our coordinate system right here. And right in the middle of the dumbbell, that's where we're going to put our origin. Okay. So, my center of mass is equal to the sum of Ri Mi divided by the sum of Mi. And our sigmas, once again, are going to roll from I equals 1 to n, which in this case I have two pieces of mass, so this is going to be 2. Okay. So, and remember these Ri's are vectors. Did I write that over here? Yes, I did. Okay. So my Ri's are vectors. And so R1, if I label this M1, then R1 is from my axis of rotation, which I've defined as the origin here. And that is going to point out here, and it will have, let me actually delete that so the arrow isn't overlapping with the M1 subscript there. Okay, so this is going to be R1, and this is going to be R2. And so R1 in this coordinate system is going to be -1, or let's say it's 1/2 L in the negative I direction, or it's -1/2 L in the I direction. And R2 is going to be 1/2 L in the I direction, right? So then my center of mass is going to be the sum of Ri Mi divided by the sum of Mi. When I equals 1, this is my first lever arm, R1, or 1/2 L in the negative I direction, times M1. But remember that our masses are equal in this case, so I'm just going to let each of these equal M. Okay. So this is -1/2 L in the I direction times M. So here is R1 times M1 plus 1/2 L in the I direction times M. And this is R2 times M2. Okay, and then I'm going to divide that. So this is where the sum comes in. I'm going to divide that by the sum of the masses, or just 2M. Okay, and as you can see, this becomes 0, which should make some sense. If I put my origin and my axis of rotation right in the middle, and this is truly a symmetric thing, then the center of mass should be right in the middle, right at this position x equals 0. And so my center of mass lies right at the origin, which should make some sense. But what will we get if we translate the coordinate system to, let's say, let the origin lie right on m equals 1? So now where is the center of mass going to be? Well, the center of mass is a physical point in your system. So its physical location relative to the particles in your system won't change, but its vector position could change if you translate or shift your coordinate system, right? So we would still expect the center of mass to be right here, but what is that new coordinate going to be based on our new shifted coordinate system? Well, again, our length between our bars is L, right? And so if this is M1, my vector R1 times M1, well, R1 lies right at the origin. So that means R1 is equal to 0. So R1 M1 is equal to 0. R2 times M2. R2 is now this entire vector, which is L in the I direction. We can say it's in the I direction because that should be plus x, and that's minus x. I forgot to label my axes, not a big deal. And so R2 is now going to be L in the I direction times M. And so my center of mass is going to be equal to R1 M1 plus R2 M2 divided by 2m. So this is going to be 0 plus Lm in the I direction divided by 2m, and this is going to be L over 2 in the I direction, which is exactly what that distance right there is. So my center of mass hasn't changed position in my system, but its coordinate has changed based on my shifted axis. Okay, so this is how you would do a weighted average for discrete particles or discrete numbers of masses. Okay, you would just fix your origin at whatever axis of rotation you are wanting to use, and then place that origin relative to where you want the actual object you have in question to rotate about. And then you just carry out this product of each individual pieces of mass, what their vector position is along your axis. Multiply those two, the mass times the vector position, add all of those products up, and then divide by the total amount of mass. And there is your center of mass. But what about a discrete object, such as, we'll do two examples, a hoop and a disc. Okay, and these are going to be continuous objects. Actually, I lied. We don't need to do these. Yeah, I want to save these for the moment of inertia. I apologize. What we do want to do is do, for the center of mass, let's do a thin rod. And we'll let the rod have length L. Okay. And we'll claim that this is a uniformly dense rod. So in other words, the mass distribution doesn't change throughout the rod. Okay. And so if this is a uniformly uniform mass distributed rod, then we would predict that the center of mass would be right in the middle. Okay. Well, actually, let's put it this way. The center of mass would equal L over 2 question mark. Okay. So let's put the origin of our coordinate system right here. So we're going to rotate or allow this object to rotate about its left end. Okay. And that's why we're going to guess that the center of mass is right at the position L equals 2. Well, in the previous question, I had discrete pieces of mass, but here I have a continuous piece of mass. So what we do is we break up the mass into small little chunks. And we claim that each chunk has a mass dm and a width dx, since we're along the x-axis. Okay? Or you could use dr if you like, but for our purposes, since we're only moving along one axis, dx is fine. And so our center of mass, yeah, since we're using x's, let's use x's. So my center of mass along the x-axis, because now we have a continuous object, we need to use the integral. So this is going to be the integral of x dm over the integral of dm. Okay? And notice that this is that first moment. The integral of x dm is the first moment, rdm, of our moments. Right, so the 0th moment was the total mass. The first moment appears in the numerator of this center of mass calculation. And our integrals are over the entire mass of our object. So now I have this kind of integral. And each of these x's, so if I look at this particular little piece of my rod, okay, then I will have width dx and I will have mass dm, but it lies a distance x away from the origin. Okay? And so now I need to somehow translate, well, let me go back. So this is indeed a weighted average, right? So here is your function x and your weight dm. And so what I need to do is I need to somehow either translate my x's into masses so I can integrate over the mass, or I need to translate my masses into positions somehow. So here is where the idea of density comes in. So we're going to define 3 different densities. Lambda is a linear density. Sigma is a area density, and rho is a volume density. So what this means is that lambda is now. So remember what density means: mass per unit, some spatial unit, right? Most of us are familiar with the volume density, mass per unit volume, which is 3 spatial units or cubic spatial units. Whereas a linear mass density is just we're going to define this to be the mass per unit length. Okay, so if you have a really thin object where the length of the object is much larger than its thickness, then this is a really good approximation. Okay, rho, or sigma rather, is mass per unit area. So this would be like if you have a really thin sheet, you can have a lot of area without a lot of thickness, so it makes sense to think about the mass distributed across that area. And then of course rho is going to be mass per unit volume. Okay, so here's what we do with this. If this is a uniform rod, then each little piece has a constant lambda. But lambda is equal to mass per unit length, and each of these little chunks has mass dm per unit length dx. So this tells us that lambda is equal to dm dx. And now I can solve this for dm, and I can write this as lambda dx. Now I have an integration variable in terms of the variable that I have a function of. And so now I can do something interesting with my integral. And so this is going to be equal to x times lambda times dx and I'm going to write this just for completeness sake that this is an integral over this, but this is equal to okay. And so if I integrate this, I get the total mass. And so the integral of lambda dx over the entire length of my rod is going to equal my total mass. But I have to integrate over the entire length because I have to integrate over the entire mass. And so the denominator just becomes, by this argument down here, my denominator just becomes capital M, or my total mass. Draw that a little bit better. Okay. Whereas my integral is now lambda x dx. But in this case, because our density is constant, that means lambda is a constant, and I can pull constants out of my integral. So this gives me lambda times the integral of x dx from 0 to L over capital M. And so this is going to be equal to lambda. The integral of x dx is 1/2 x squared from 0 to L over M. And so this is going to equal lambda times L squared over 2m. So I'm moving the 2 into the denominator. Now, how does this work? Okay, what do I need to do here? Well, what I can do is I can notice that if I look at the entire length of the rod, I will have a total mass m over a length L. So not only does lambda equal dm dx for each little mass element, but it also equals my total mass over my total length. So if I make this substitution that lambda equals m over L, then one of my L's here cancels with this L here, my m cancels with this m, and lo and behold, we get that our center of mass is at the position L equals 2. Now, I have been very, very lax with my unit vectors, but all of my x vectors here are going to be in the I direction, and so technically all of these integrals are in the I direction. And there you have it. Okay, so that is how you would approach a center of mass calculation when you have a continuous object. Okay? And so now on to the moment of inertia. Okay. So the moment of inertia, I, is the second moment, or r squared dm integral over m. This is the most general way to calculate it, but for discrete okay. So let's start with the discrete system, and let's actually do our dumbbell again. And by the way, note that this is a scalar, not a vector. Okay, so your moment of inertia plays the same role in rotation that mass does in linear motion. Okay, so if you think about the word inertia, its resistance to a change in its motion. Mass, m, plays the role of the resistance or an object's resistance to its change in linear motion. In other words, a resistance to being accelerated. And the moment of inertia plays the same role in rotation. It's the resistance of an object to angular acceleration. Okay. So let's come back to our dumbbell example. And let's calculate the moment of inertia of the dumbbell. Now, this is where, so for your center of mass, remember, the physical position of the center of mass did not change. If you switched coordinate systems or translated your coordinate system, then you might get a different answer, but it would be in the same place within the physical object. This is not true for the moment of inertia. Okay, so your moment of inertia, it is crucial that you understand which axis you are wanting to rotate your object about. So let's start with the central axis. So I want to rotate my system, maybe say like this. So think of like twirling a baton in your fingers, and you're holding the baton in the middle, right? So each of these has mass m, and we'll call this mass 1, we'll call this mass 2, and we'll again assume the condition that m1 equals m2. Okay, so my moment of inertia in this case, so let's be very formal once again. This is x in the plus x direction. This is x in the minus x direction, and this is a length L. Okay. And so my moment of inertia is going to be the sum of xi squared times mi. So this is going to be, for m1, the vector associated with m1 is r1, which once again is right here. And my vector for r2 is right here. And so with that in mind, r1 is going to be negative L over 2. Oof, let's write that a little bit better. In the I hat direction, R2 is L over 2 in the I hat direction. Okay. And my squareds become, well, actually I need to fix one thing. So these should be x's now since we're only in the x-axis. So x1 squared is equal to x1 dotted into itself. So when I get a scalar from when I get a squared scalar, that's almost always going to be the dot product of a vector with itself. Okay. So this is negative L over 2 I hat dotted into negative L over 2 I hat, which is L squared over 4. And x2 squared, by the same token, is also going to be L squared over 4. You can prove that for yourself just by doing the exact same thing we just did right here, only with this vector right here. Okay? So my moment of inertia is going to be L squared over 4 times m plus L squared over 4 times m. And so this is going to give me L squared m over 2. Okay? So typically your moments of inertia are going to involve a square of some distance and then also involve mass. Okay, so if you look at the table for moments of inertia in the book, you'll find, well, let me start by saying this will often be written by you write your mass first. So this would be ml squared over 2. If you look at your table for moments of inertia in your book, you'll find all sorts of different combinations for different objects being rotated around different axes. But we will do one specific approach or one specific object, and that is the disk. We will also do the hoop, but the disk is going to be the most in depth of the calculations. Okay, but before we do that, this is example one. What if I instead try to rotate my dumbbell around one end? So what if I make my axis of rotation around this dumbbell? Okay. And remember that your moment of inertia is an object's resistance to its angular acceleration. So, as a result, if our result for the moment of inertia here, let's call this moment of inertia 1, this will be moment of inertia 2, if I2 is larger than I1, then what that means is it's going to be easier to spin in this configuration than for this configuration. If the situations are reversed, then those will be reversed. If I2 is less than I1, then it'll be easier to spin our configuration in situation 2. Okay, so just be aware of that. And so now we want to do the calculation. And our vectors, well, I don't have a vector associated with I1 because I don't have, R1 lies right at the origin. So R1 is equal to 0. And R2 is equal to Li hat. Okay, so now we can calculate our moment of inertia. Well, I don't need the summation anymore because I can just add. Okay, so R1 squared is going to be 0. R2 squared is going to be L squared. Okay, so the moment of inertia for this system, when I try to rotate it about one end, it's just equal to my mass times my length of my rod squared. Okay, so I2 is indeed bigger than I1. So that means I1 is easier to spin. Okay. So that's a discrete example, well, two discrete examples. All right. And so now for the hoop. And so a hoop is defined as, imagine this is a perfect circle. Okay. So a hoop is defined as if I have some thickness of my hoop dx, or dr if you will. My radius of my hoop is much larger than my thickness. Okay, so this is the definition of a hoop. And so I want to calculate the moment of inertia. And we're going to basically let this roll like a tire. So what that means is there's like a central axis coming out, and we are rolling about that axis like this. Okay? So if we have a central axis, then each piece of the hoop, I can break this up into infinitesimal pieces, and each piece will have dm, and they each lie a distance capital R away from the axis of rotation. So this is going to be equal to the integral, pardon me, of r squared dm, but this r squared, each of these is capital R. And this is over the mass of the hoop. But since each mass piece lies at the same distance away, this r squared is constant, so it can come out of the integral. And I just integrate my way around the hoop. And so I just take this little mass piece dm and add this little mass piece dm and go all the way around the hoop. And then when I add up all of those little dm's, I just get the total mass of the hoop. So this is r squared times m, most often written as mr squared. Okay? So this is the moment of inertia of a hoop about central axis. Now for the disk calculation. So suppose I have a disk, like a hockey puck, and I want to spin it about its central axis as well. Okay, so I want to make it spin, like a top maybe. I want to calculate the moment of inertia. It doesn't really matter how we spell disk. It can be spelled with a C or a K. It doesn't matter. But I've already started with a C. Okay. So I have to perform this calculation This is not necessarily the simplest procedure, but this is the way it's done. Okay, so we have to come back to this idea of our densities. Okay, and so I am going to concentrate on the volume density. So if mass per unit length is dm dx, mass per unit area is dm dA, and mass per unit volume is dm dV. Okay? So we're going to use this idea that rho, and we're going to assume this is uniform density. Then rho is going to be equal to dm dV. But for a disk, dV is going to be equal to an area element on the disk, or 2 pi r dr, times the height of the disk, let's call it h. I didn't give myself enough room. And this 2 pi r dr is your area element of the circular face. So if I'm looking at my hockey puck face on, then actually let me draw that a little bit bigger. And so if I have an area element of a circular part of the disk, okay, so this circular part has radius r, it'll have thickness dr, and if I need to find an area element such that when I integrate around the entire disk, I get pi capital R squared if capital R is my total radius of the disk. Okay. So 2 pi r dr, if I integrate this from 0 to r, this gives me pi times r squared from 0 to r. And this gives me pi r squared. So we know that that's the correct area element. And then to get the volume, I just multiply that by the height. So this is why the volume element is what it is. And so now I can substitute that into my integral. But I need to do something first. Okay, so remember that rho is dm over dv, so that means that dm is equal to rho dv. So I need to include a rho here. So rho times 2 pi r dr h. Okay, and a lot of this is constant. Rho is constant if we have uniform density. That implies that rho is constant. Of course, 2 pi is constant and h is constant. So this is going to be 2 pi rho h integral of r squared times r is r cubed dr from 0 to capital R over the entire disk. Okay? And so this is going to be 2 pi rho h times, cutting to the chase, the integral of r to the third is r to the fourth over 4, evaluated from 0 to capital R. This is capital R to the fourth over 4. So this cancels with a 2 down here. So I'm going to get pi rho h r to the fourth over 2. And you might go, okay, that's not very enlightening. And it's not terribly enlightening. But what we can do now is resubstitute with rho. So for a disk, your volume for your disk is pi r squared times h. So my rho is equal to my mass divided by my total volume. And so if I substitute that, this becomes pi times rho, which is m over pi r squared, h times h r to the fourth divided by 2. And so my pi's cancel, my h's cancel, and my r squared cancels with 2 of my r's and r to the fourth, so I'm left with r squared. And so I get mr squared over 2. This is the moment of inertia of a disk if you are trying to rotate it about your central axis, again like a tire or a top. It's a beefy calculation, but there it is. Okay, so there is your center of mass and your moment of inertia calculations. Whew. And just to reiterate one more time, okay, your moments, your zeroth moment when n equals 0 is your total mass. It just becomes dm. When n equals 1, rdm becomes the numerator in your center of mass calculation. And when n equals 2, this is your moment of inertia. Okay. Whew. It's a lot of math, but I hope you followed it. And if you can follow these examples, then you'll be well on your way to replicating any of the center of masses as listed in the table. Really, all of your standard introductory textbooks carry a similar table, so you'd be well on your way to being able to replicate those. All right, folks, we will see you next time.